Thank you, your ears, for the kind introduction, and I'm really looking forward to visit the University of Sydney and the Total Body PET facility there and work with you on our project. I'm going to also briefly discuss a little bit about that potential in my slides. So my talk today on this exciting 7th webinar of your exceptional series for total body PET imaging is going to focus on dynamic multi-parametric PET imaging and how total body can actually elevate its potential, particularly for oncology. So these are my disclosures. I have nothing to disclose in this talk. The components of my talk is going to be two. The first one, we're going to emphasize on the value of dynamic and multi-parametric PET imaging in oncology and for whole body and total body PET imaging. And then I'm going to also talk about the importance of cost effectiveness in total body PET imaging and how we can enhance clinical adaptability of this technology to maximize the benefit for oncologic patients. The common denominator of both of those components is, as I said, the clinical adaptability and our objective to widely disseminate the benefits of this technology across the world. So let's first discuss about the value of dynamic PET imaging as generally and also in particular to whole body and total body PET imaging for oncology. So why dynamic imaging? Traditionally, we acquire data in PET imaging in a static fashion. That means we scan a particular field of view, either a limited or a total body field of view once in time after injection. And then we take the data, we average them, and we take absolute measures of the activity concentration normalized by the lean body mass and the dose that we think we have injected, which may not be so accurate. So although this is a well-established metric in nuclear medicine, the standardized uptake value, it's considered semi-quantitative. And the reason for that is that we have to assume a particular time at which we obtain the activity concentration. And as we know, the concentration is dynamically changing due to the kinetics and the molecular interactions within our body for a particular tracer. And also we have to normalize it based on the dose that we have injected. Sometimes though, some of that dose may not get into the circulation system. And also we have to average that over the body weight or the lean body mass, which may not be exactly accurate. So to overcome these problems, another suggestion is to actually acquire the data in a dynamic fashion, which is basically the inherent type of acquisition in PET. But instead of actually taking the dynamic data and averaging them in a single time frame, we can actually bin them or sort them in different time frames and process each of those time frames separately to determine the kinetics of the radiotracer activity, contribution, concentration in the human body after post-injection. And by doing so, we can actually obtain parametric images beyond the standardized uptake value, such as the PAT-like images. And this is something additional in terms of information for the physicians that can help them identify more subtle features of tumors or other diseases. However, because of the complexity of this protocol, we'll just have to do it dynamically. It has been constrained mainly in research for brain and cardiac PET and has not been actually translated to oncology, where we need to obtain data in a whole body fashion. The main method that we use to analyze those dynamic data is the PAT-like graphical analysis method because of its robustness and simplicity. And the reason for that is because it's basically a linear model that allows us to provide estimates of the tracer net uptake rate and total blood distribution volume, Ki and V as we denote them in those slides. Then there are two flavors of the PAT-like model, the standard linear PAT-like model, where we take our measurements of the activity concentration over time, C, and the activity concentration in the plasma, Cp, and the integral of that, and we formulate them into this equation, and then we, as you can see, the linear equation, we can then fit the data from the multiple time frames and obtain the Ki or the slope and the intercept or total blood distribution volume parameters here after a certain T-star time post-injection, which is usually 5 to 10 minutes after equilibrium has been established in the tracer for a particular tissue. However, this approach, as we will discuss later, assumes that there is irreversible uptake, and it's very well suited for FTG. But even for FTG, some cases, the uptake may not be strictly irreversible. We may have a leakage of uptake after it gets absorbed from the tissue back to the blood. And in that case, we may want to use a more generalized flavor of the same padlock model, which includes this additional exponential nonlinear term here, which quantifies the extra parameter of K loss, which actually denotes the efflux rate constant of the tracer from the tissue back to the blood. But that's a nonlinear model and suffers from noise. But we will talk later about how we can overcome these issues. So the main advantage of dynamic PET imaging and padlock analysis is that you can quantify Ki that takes into account the dynamics of the tracer and also the dynamics in the plasma, while SUV does not. So traditionally, we acquired data over time, and you can see here the conventional methods were actually limited to one field of view. So back in the day where we had a limited axial field of view scanners, we could only scan a particular part of the body, and that was typically was the heart or the brain. But we were limited to the small axial field of view by doing so. So we couldn't translate the benefits of dynamic and parametric imaging into the whole body, which is necessary for oncologic applications in particular. So by taking advantage of the latest technology trends, we were able to scan the patient faster from head to toe and then come back to the head and scan again. And that's how we can now obtain multiple bed passes, even if we have a limited axial field of view systems. So this protocol is also feasible, not just with total body, but also with limited axial field of view conventional low-cost systems nowadays. But of course, because of the fact that we have to scan faster and come back and scan multiple times, we have significant time gaps between the acquisition, and we also have lower signal-to-noise ratio and lower counts. So this is, but this protocol actually allowed us to apply dynamic PET imaging and parametric imaging in oncology for the first time, just before the advent of total body imaging. However, with the advent of total body PET scanners, of course, this application becomes much more trivial and feasible because we can obtain the same data now with a very high signal-to-noise ratio, and we can just have one only bed per pass instead of multiple beds as we're showing here. And also we can have compartmental kinetic modeling, not just pathographical analysis. Compartmental kinetic modeling takes advantage of higher order differentials equations in your tracer kinetics to give you even higher order information for the kinetics of the tracer, which can be useful sometimes. But on the drawback, this has a relatively higher manufacturing cost, this technology of total body PET, because you really need to use a large volume of detectors to cover the entire body. And also that means it's not yet clinically adaptable in a large scale. Whereas with the dynamic whole body PET imaging technology, we still is widely available at low cost. However, it has a limited field of view per pass, and also it's low sensitivity and signal-to-noise ratio. Here is a review of kinetic modeling and dynamic imaging applications in oncology before the advent of total body, and how total body can also benefit from this technology. And I urge you to go and look at that review paper from Antonia Dindragopoulos-Strauss from Heidelberg. So how is the initial application of dynamic PET imaging in oncology begin with? So we begin with a single bed dynamic scan over the heart to obtain the input function that is necessary for dynamic analysis. And then we start doing conventional whole body scans multiple times. Here is the first pass. And once this is completed, then we return back to the head and we conduct a second static whole body pass. And by doing so, if we repeat this n times, we can obtain at the end multiple passes, let's say n passes. And then all of a sudden for each of those passes, we have dynamic data at every bed position. So we can analyze the dynamic data at every bed position sequentially. And then at the end, we can stitch together those dynamic data from all the beds and obtain a parametric image of the whole body. So there's a bit of a lag here in this animation. So again, if we want to do this protocol and a standard of care scan protocol, it's very difficult because as a dynamic acquisition, we have to acquire data for a long time after injection, from 0 minutes post-injection to maybe 60 or even 90 minutes post-injection. But that's important if we want to capture all the kinetics of the tracer. So this is one of the major limitations for the clinical adaptability of this technology, the fact that we have to trace the activity concentration over a significant large amount of time post-injection, which will significantly impact the comfort of the patient and the throughput of our clinics. However, there are ways to accelerate that, and I'm going to talk about this in the next few slides. So first of all, we can combine SUV and PATLAG imaging from the same data set. And this can be done by, after we acquire the data for every pass, we can actually add the data together from sequential passes and obtain SUV images, as I'm showing you here. At the same time, we can use the same data, the dynamic whole body data, and analyze them based on the kinetic modeling analysis that we use, such as the PATLAG analysis, and obtain the parametric images using a population-based input function. So we can actually omit the first 1 hour of scan. We can bring the patient into the scan after 60 minutes and then start scanning dynamically. And the beauty of PATLAG analysis is that in order to estimate our tracer net influx rate and our blood volume distribution, we only need the integral of the input function. So we only need the input function, and a model of that can be obtained from a population studies, as I'm going to show you in the next slide. So literally, this application protocol actually allows us to reduce the total scan time from 60 minutes down to 20 or even 15 minutes. Even for a short axial field of view system. The same protocol can also apply for total body imaging. In that case, though, we don't have to have multiple beds. We just have 1 bed per pass. But still, we can utilize the population model to skip the scan for the first 1 hour. And here is the way we propose constructing our population model for our input function, for our tracing concentration in the blood. This can be done by obtaining multiple image-derived input functions from multiple patients, then correcting for time delay to align their peaks, and then make sure we scale them to match their tails, and then average out to obtain a single model of the input function, which we can then scale prospectively to any new case that we have to scan based on the later acquisition of the data after 60 minutes. And this will allow us to extrapolate the missing input function for the first 1 hour that we did not scan. So here I'm explaining the different steps that I just described you. And by repeating steps B, C, and D for different patients, we can actually scale that model to each patient prospectively and reduce the total scan time from 1 hour, 90 minutes down to 20 or 15 minutes. Here's a clinical demonstration of the first scan that we had performed with this method. This is a traditional SUV scan. You can see obtained after 60 minutes post-injection with FDG. And this is the same patient undergoing the new protocol where we dynamically scan the patient multiple times with a limited axial field of view system. And then we can take the data together, add them up to obtain the images. Either on the addition can be done either on the image domain or on the sinogram domain, the raw data. The results are very similar. And then we can also, the same data, analyze them by PATLAG and obtain the PATLAG analysis. This can be done indirectly by looking at the reconstructed images or directly, as I will show you later, to improve the noise. And the same method can also apply for total body bed imaging, except for the fact that you only have 1 bed transition per pass, and therefore much better statistics, as I will show you in a few slides later. So another important thing I wanted to stress here is that we always assume most of the times that in standard PATLAG analysis is sufficient for FDG. But as I said before, sometimes PATLAG assumes that the tracer is irreversibly absorbed by tissue, such as the FDG, but that may not be the case in some tissues or for some tracers. And the reason for that is because sometimes we have leakage of activity coming from the C2 compartment, which denotes the activity that is trapped in the tissue, the tracer concentration that is trapped in the tissue, back to the free compartment and the blood. So K4 is assumed to be 0 in padlock, but sometimes K4 is not 0. And here is how this is usually reflected in our data. When we acquire the data and we plot them based on the padlock assumptions, instead of obtaining a linear curve, we may obtain this curve here, the blue or dashed curve, that actually, as you can see, the slope is reduced as we go further and further as we delay the analysis to time periods further delayed in respect to injections. So you can see that if we try to fit that curve, the slope will be underestimated because it's not linear. However, if we apply the generalized padlock model, then this curve is corrected. We get linear data, and then our slopes are coming closer to the true data. So this was based on simulations that was designed based on real K parameter values, kinetic parameter values that we have obtained from human scans. And you can see the impact of the generalized padlock analysis versus the standard padlock in restoring the true value of the Ki parameters and the blood distribution parameters. And here is an example of reported literature from the past where they have actually reported significantly high K4 values even for FTG. And that's why we stress the need that sometimes standard padlock may not be sufficient. And this is part of the project that we have with Yorgos, University of Sydney. We plan to implement this technique on total body PET data now that we have even better signal-to-noise ratio with total body PET data, and see the benefit that this may have in assessing properly treatment response for cancer patients. So moving forward, the first evaluation with this method was done on simple limited action field of view scanners. We scanned a patient for the first 6 minutes, and then we scanned 45 seconds per bed, multiple passes. And then we obtained 15 whole body passes over a period from 0 to 90 minutes. And then we choose only 4 of those passes, and we looked at the Ki values that we estimated as we slide the window, this 4 passes window over time. And we noticed that the Ki was varying. It was supposed to be constant. It was not constant at all. And this actually indicated that we may have a violation of the assumptions of the standard padlock model, and that highlighted the need of using a non-linear, more generalized flavor of padlock, as I showed you before. So this is a quick example of why even parametric imaging sometimes may not be quantitatively as accurate as we would hope to, and we have to always ensure that the kinetic parameter assumptions are not violated by our model. The other thing I wanted to highlight is that another advent of technology, apart from total body, that helped us with compartmental kinetic modeling analysis and padlock analysis was the advent of time-of-flight technology and point spread function resolution modeling technology. As you know, or some of you may know, when we perform PET imaging, we are actually estimating the position of interaction of 2 gamma photons that are annihilating. They are at 180 degrees apart, and we only know that the interaction happened along this line, but we don't know exactly where the interaction took place. But by measuring the time of arrival of the first detector, or of the first photon that got detected in the first detector and in the second detector, and taking the difference in time, then we can more precisely estimate approximately the position of interaction along that line. And this hugely helps the signal-to-noise ratio recover in our final reconstructed image. The other potential technology that can help us improve partial volume effects and resolution is by actually modeling those effects if we in advance know their physics behind it. So such as in this case, we know the FTG has a certain positron range and also an collinearity, which means that it's not exactly 180 degrees apart. There can be some uncertainty in that angle of incidence, and this creates some errors and some blurring, which we can model and correct for during reconstruction. So By taking advantage of these technologies in our latest generation scanners, even the limited axial field of view, as well as the total body scanners, we found out that our estimates of the kinetic parameters are more accurate, and the contrast to noise ratio in the images is also significantly improved. And this is particularly also important for generalized path-like imaging, which is nonlinear and suffers more from noise. So here we're showing you data where you can see that when we use time of flight and PSF, we get better target to background ratio contrast and contrast to noise ratio for 2 cases. We get significantly better results as opposed to using only one of them or using none of those technologies. Another latest advancement that we want to highlight is the advent of direct PET image reconstruction. So traditionally, what we obtain is, when we do dynamic imaging, is a set of dynamic PET raw data. And here I'm showing you examples of the sinograms, dynamic PET sinograms. Each one of them corresponds to a certain time frame that we acquired post-injection. So the traditional approach for processing those is to first reconstruct individually each one of them, obtain the images that corresponds to each one of those sinograms, and then on the image domain, apply the path-lag analysis and the input function to obtain our KI images, and then smooth them to obtain the lesion detectability, improve the lesion detectability. And here's a comparison in a simulation study where we, of course, know the true KI and the true distribution volume, and you can see how it compares against the actual noisy data, the estimated and the post-smooth images. You can see that the data are pretty noisy, and sometimes we even get false positive indications because of the high noise. However, there is a way where we can incorporate inside the reconstruction this path-lag model and directly reconstruct the parametric images without having to go first through the dynamic image domain. And we can directly go to the parametric image domain. And this significantly helps handle the noise and improve the signal-to-noise ratio in our final parametric images and avoid having false positive lesions, as you can see here in this example. And here is an example of a study where you can see the full length of this analysis, where we did the traditional SUV scan. Then we added the last 4 dynamic frames to obtain a synthetic SUV and compare it against the traditional SUV. You can see it's very close to what we will have get with a conventional SUV, except from the fact that this was scanned on a different day than this case. And then you can also see the path-lag analysis. If you do indirect analysis, you suffer from high noise, but if you do it on a direct reconstruction, you significantly improve the noise and the signal-to-noise ratio and avoid having issues with false positive lesions. And even with generalized path-lag analysis, the last column, where you expect to have higher noise, just because you're doing it in a direct fashion, you still get even better contrast without affecting much the noise level. So this last column generates the higher signal-to-noise ratio for this case. Moving forward, I would like to also stress that we did a systematic analysis on patients to see how the dynamic and parametric imaging affects lesion detectability in oncologic patients. And we found cases such as here in the liver, where we couldn't obtain any lesion contrast with the traditional SUV, but with path-lag KI imaging, we saw a high focal uptake in this region that was later confirmed with pathology. And this is also a case where we had a false positive indication in the liver, which we didn't see in the path-lag analysis. So path-lag also helped improve the true positive and reduce the false negative cases and false positive cases. So although the reduction was not impressive, there was some significant improvement in sensitivity and accuracy by applying parametric imaging as opposed to standard SUV imaging. Here is another study where investigators try to limit the acquisition to reduce scan time, and you can see how it actually improved the correlation. But if you go too low to 30 minutes, then you start facing issues. So moving forward, this is a case where we actually obtained through compartmental modeling in comparison with path-lag imaging, and we could see the benefit of having both in whole body dynamic imaging. So for the interest of time, let me move forward to the latest part of the talk. So what I want to highlight here is the fact that by doing whole body parametric imaging without a standard generalized padlock, we can have robustness to noise, but we actually sacrifice a little bit in accuracy. With generalized padlock, we're more quantitatively accurate, but we're more sensitive to noise. So all these challenges can actually be addressed with direct 4D reconstruction, generalized padlock modeling, motion compensation techniques, and population-based models that I discussed before. However, they can also all be addressed by using total body PET imaging. And this is really the game changer for dynamic PET imaging in oncology. And I'd like to stress the importance of doing total body PET imaging for oncology. Now, my last slides is going to focus on cost effectiveness of total body PET for oncology and why this is important to improve the clinical adoption of the method. Here is the history of evolution in PET. First, we improved the spatial resolution. Then we opened the angle of acquisition to obtain 3D acquisitions, then improve the geometric sensitivity. And then we also used time of flight to further improve the signal-to-noise ratio. However, with total body PET imaging, we really improved further the image quality and break the barriers of the previous technologies. This was historically the first one, the PET Explorer and the United Explorer from UC Davis, that allowed us to go up to 2 meter long field of use. Then we have the Quadra from Siemens that offers us about 1 meter long scans with very good sensitivity of 176 counts per second per kilobecquerel. And now we have even GE offering systems of the same characteristics. The two main advantages of total body is first, the larger area that can be scanned simultaneously with obvious advantages for dynamic imaging, and also allowing us to obtain our dynamic protocol in a much faster way. And the second one is the enhanced 3D PET sensitivity because of the larger coverage and solid angle coverage. So you can see here that now we can obtain much higher sensitivity just because we have a larger solid angle coverage, and this allows us to obtain ultra fast acquisitions where we can actually see the root of the tracer in the body. So here is some literature review that I encourage you to look for the benefits of dynamic PET imaging in clinical oncology and total body PET imaging. So to move forward, with long axial field of view systems now, we can cover the same area in a larger space. So this allows us to obtain better sensitivity. This allows us to get better image detail in our total body systems. Ultra low dose scans with only 0.15 millicurie FTG scan the same image quality with much shorter time, as Andrew had showed before, and also ultra fast dynamic imaging. So you can obtain multi-compartmental modeling, not just padlock, with very high signal to noise ratio. Here's examples where we have applied kinetic modeling and total body PET imaging, and you can see that we can even select different kinetic models for voxels because you have such a high signal to noise ratio to even better improve your accuracy when estimating your model selection for your kinetic model. Or you can see lesions that you couldn't see before, as we show in this case. And as before shown by Andrew, we can actually obtain not just SUV and KI images, but also K1 parameters and other parameters, such as V0 with very high signal to noise ratio. Or we can wait much longer over time to obtain higher contrast images. So the last thing I wanted to mention is that you can also obtain connectivity studies where you connect cancer with expressed in, for instance, in the liver with brain neurological disorders, just because you simultaneously scan multiple areas of the human body that was previously not possible. So with that, I would like to conclude my work.